Before we get to understand mathematical cryptography, one needs to have a solid number theoretical background. Therefore, we'll start by defining sets of numbers and their links with roots of polynomials. Number theory starts with the set of natural numbers, which we denote n. Notice here that I exclude 0 from this set, but it's not a big deal for us. It is natural for us to work with this set of numbers as we need to count things on a daily basis. However, we run into problems as soon as we try to solve the simplest linear polynomial equations using only natural numbers. As an example, the equation 2 plus x equals 5 has a solution in the natural numbers, namely x equals 3. But the similar equation 5 plus x equals 2 fails to have a solution in the set of natural numbers, because if you add a natural number to 5, the result is always greater than 5 and never hits 2. So in order to solve this equation, one needs to create a new set of numbers bigger than n, which includes all the positive and all the negative and 0 as well. Z here refers to the word Zahlen, which in German means numbers. Notice, however, that z is not enough to solve an equation like 7x equals 5. Said in other terms, there is no integer x such that 7 times x is equal to 5. This is mainly because 5 is a prime number and the only divisor of 5 are 1 and 5, and that 7 is not a prime divisor of 5. In order to solve this equation, and more generally equation of this form, one needs to invert non-zero integers and so to augment z to get the set of rational numbers, which we denote by q. Now, one natural question is the set of rational numbers enough to solve every single equation? The answer is no. Indeed, I hope you all remember from high school algebra that the equation x squared minus 2 equals 0 does not have irrational solutions because square root of 2 is not a fraction. Said in other terms, square root of 2 is different from every single fraction of the form p over q, where p and q are integers. We will not prove this fact here, but we'll probably do so in a future lecture. In practice, we define numbers by their decimal expansion. For instance, the beginning of the decimal expansion of square root of 2 looks like this. And as you can see, one can barely notice any pattern in the decimal expansion of square root of 2. However, the decimal expansion of 3/7 is periodic. Actually, the decimal expansion of every fraction is periodic as well. Do you see why? Conversely, every number with a periodic decimal expansion is actually a fraction. We will show this on an example. Indeed, if you consider the number x defined by 0.12345, 345, 345, and so on and so forth, we would like to get a fraction which represents this number x. What we do is very simple actually. We multiply x first by 10 squared. We get 10 squared x is 12.345, 345, 345, and so on and so forth. And if we do the same thing with another power of 10, we take here 10 to the 5, and we get 10 to the 5 multiplied by x is 345.345, 345, and so on and so forth. And now if we subtract both of these equations, we get 10 to the 5 minus 10 squared of x equals 12,345 minus 12. And actually, now if we divide this number by this number here, we get x as a fraction. What we have shown here is that rational numbers are exactly those numbers who have a periodic decimal expansion. From this, we deduce that square root of 2 has no period actually, because we have seen that square root of 2 is not a rational number. I claim that it is now obvious how to extend q to get to solve equations like the one here, x squared minus 2 equals 0. Indeed, we augment q to include all possible decimal expansions and not only those that are periodic. We get, informally, the set of real numbers, which we denote r. Now that we can work with the set of real numbers r, we see that many more equations are solvable. For instance, if you take x squared minus 3 equals 0, we see that plus or minus square root of 3, which are numbers in r, are solutions. More generally, equations of the form ax squared plus bx plus c equals 0, where a is different from 0, and one more condition, b squared minus 4ac is positive, have two solutions, namely x equal minus b plus or minus square root of b squared minus 4ac all divided by 2a. Now we ask the same natural question: is the set of real numbers enough to solve all equations? The answer is still no. As you probably know from high school algebra, not all quadratic equations have solution in R. For instance, the equation x squared plus 1 equals 0 does not have solution in R because this is equivalent actually to x squared equals minus 1, and we know that a square is never negative in R, which means that this equation is impossible. Now, a tour de force technique is to suppose there is actually a number which we denote I, such that I squared equals minus 1. By doing this, we get to construct a new set of numbers which we denote C and call the set of complex numbers. You probably know this set from high school algebra. Now the good question is, are we going to do this eternally, constructing sets over sets to get to resolve every single equation? Well, surprisingly, the answer is no. And believe me, this is incredible. C is actually enough to solve every single equation. We call this result the fundamental theorem of algebra, which states that every non-constant polynomial with coefficients in C has a root in C. We say that C is algebraically closed. In this first course, we are mostly interested in natural numbers, integers, and fractions. We will say that a polynomial has natural solutions if they belong to n, they have integral solutions if they belong to z, and irrational solutions if they belong to q. Let us try to find natural, integral, or rational solutions to the following polynomial: 3x cubed minus 11x squared minus 24x plus 20. Notice that this polynomial has integral coefficients. So if n is a natural number such that p of n is 0, which we can rewrite as n times 3n squared minus 11n minus 24 equals minus 20. This actually means that if n is a root of the polynomial p, then n must be a divisor of minus 20, which means that n belongs to the set 1, 2, 4, 5, 10, and 20. By trial, we can see that the only root of our polynomial from this list is n equals 5. We would like now to find integral solutions to the polynomial p, which means n in z, such that p of n is 0. In the same fashion, we find that n is a divisor of minus 20, but this time n is an integer, which means that n belongs to the list of plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. By inspection, we find that minus 2 is the integral solutions to the polynomial p. Our polynomial is of degree 3, so it must have another solutions, and let's try to find out if it is rational or not. Indeed, if p of m over n is 0, we can rewrite this as 3 times m over n cubed minus 11 m over n squared minus 24 m over n, plus 20 is 0. If we multiply both sides by n cubed, one gets 3m cubed minus 11 m squared n minus 24 m n squared plus 20 n cubed is 0. Now in the same fashion as before, we rewrite this as follows. M times 3m squared minus 11 mn minus 24 n squared is equal to minus 20 n cubed. But we can rewrite this as n factors 20 n squared minus 24 mn minus 11 m squared is equal to minus 3 m cubed. Ooh, scary movie, but do not get too scared because this first line means that m divides minus 20 n cubed, and this second line means that n is a divisor of minus 3 m cubed. I claim that we're almost done actually. The fact that m divides minus 20 n cubed implies that actually m is a divisor of minus 20. This is true since m and n share no common divisors. This means that m belongs to the list plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. The same argument works with n actually, since we know that n is a divisor of minus 3m cubed. This means that n must divide 3, and so n belongs to the list plus or minus 1, plus or minus 3. Now as a matter of inspection, and we find that m over n equals 2/3 is the last root of our polynomial. Thus we have shown that 5 minus 2 and 2/3 are the roots of our polynomial. By a theorem of high school algebra, we can show that p of x can be rewritten as 3 times x minus 5 x plus 2 times x minus 2/3. Our first lecture ends here, and notice that in the course of finding the roots of our brave polynomial p, we have used the theory of divisibility that we will study in depth in future lectures. Thank you for listening.